There are 6 Mega Man games on the NES, and the development history behind the third entry in the series is perhaps the most interesting. Over the course of 6 years, we see the releases of these 6 titles reflect contemporary NES cartridge technology, including bank switching hardware, as we move from off-the-shelf components to the MMC1 mapper chip, and finally to the MMC3 mapper chip in the remaining 4 games. The first and second games were released 1 year apart. Capcom didn't greenlight a sequel at first, but the dev team agreed to work on Mega Man 2 on their own time. The second game was a love letter to the franchise that also turned it into a franchise. Both Mega Man 1 and 2 were directed by Akira Kitamura and programmed by Nobuyuki Matsushima. Now here's where the timeline gets interesting. About a year passes before the team starts work on the third game because Kitamura left. Let's say work started somewhere around Q4 of 1989. Tadashi Kawana is listed as the programmer for Mega Man 3 and most likely inherited the Mega Man engine previously developed and enhanced by Matsushima. As far as their responsibilities at Capcom at the time, Kawana was one of the programmers for the arcade version of Strider, released in March of 1989. CP System 1 hardware uses the Motorola 68K processor. I don't know if Kawana had any prior NES or 6502 processor experience before Mega Man 3. Matsushima was one of 2 developers for Street Fighter 2010 The Final Fight, also an MMC3 title, and that game was released in August of 1990, 1 month before Mega Man 3. The 2 programmers were busy on independent projects up to the release of those projects in summer of 1990. So I assume it is safe to say that Tadashi Kawana was tasked with taking someone else's code that had already seen one revision, converting it to MMC3, adding MMC3 embellishments, and implementing new designs from the design team while being told, get it done yesterday. Do all of this while maybe not having any prior experience with the NES or 6502. You may think this request is ridiculous, and it is, but welcome to the world of software development. So we're going to analyze and fix some of the buggy mess that we find in the stage select screen and pause menu, but we are going to do so while recognizing that it is perhaps a miracle that the game not only works, but is also fun to play, given this assumed development history. Our journey begins with the MMC3 mapper chip. We briefly discussed this chip in episode 3 of Talk and Code. One of the biggest features is its ability to generate an interrupt once a desired count of scan lines has been reached. This is a pretty big deal. Up until this point, many NES games needed to split the screen in such a way that a heads-up display with gaming information remained locked into place while the rest of the screen could scroll. Super Mario Bros., Castlevania, Ninja Gaiden, The Legend of Zelda, Zelda 2, and Mike Tyson's Punch-Out!, yes, that game scrolled too, were among the many games that made use of the Sprite Zero hit in order to determine when to allow scrolling to begin as the PPU draws the game down the screen. Each of these games uses the coordinates for the sprite in the first slot of OAM, Sprite 0, to indicate a seam. Once the PPU has reached Sprite 0 and thus Sprite 0 is hit, it is time to let scrolling happen. Since we have to wait for the Sprite 0 hit to occur before allowing scrolling to take place, the CPU is put in a loop to do nothing but wait for this to happen as the PPU draws the game to the television. The loop reads the PPU status register over and over until the bit that holds the Sprite 0 hit flag has been set. Each orange box you see indicates a read of the PPU status register inside that loop. While this works, it requires the game to take a hit in performance. The time the CPU could spend working on logic for the next frame is sacrificed in favor of the programming equivalent of asking, "Are we there yet?" over and over again. The MMC3 mapper chip and its abilities to count scan lines and interrupt the CPU means that the game can be programmed to jump to a new place in code the moment the interrupt occurs, handle some graphics instructions, and then return to what it was doing. Look no further than the MMC1-based Ninja Gaiden using the Sprite 0 hit versus the MMC3-based Ninja Gaiden 2 using the interrupt, or IRQ. The original game has to wait on the Sprite 0 hit to occur to know it is time to handle scrolling beneath the HUD. Meanwhile, the second game can let the CPU go about its business during this same period of time, fire an interrupt when we reach the desired scan line, jump to a place in code to handle scrolling instructions, and then return to what it was doing. This is, "Are we there yet?" versus, "Excuse me for one moment, please." And why stop there? We talked about multi-directional scrolling in Super Mario Bros. 3, and this very same Ninja Gaiden 2 example has parallax scrolling. 2 examples of some fancy techniques that are easy to do thanks to interrupts courtesy of the MMC3. Mega Man 3 performs a similar screen split as the Mario 3 match game, but unfortunately has a minor bug that is quite noticeable. We'll address the infamous Mega Man 3 stage select screen later. But first up is this. The game scrolls horizontally, but the pause menu for weapon selection scrolls up vertically. There are a couple of bugs here, as well as a graphical design flaw. Let's talk about the horizontal and vertical scrolling in Mega Man 3 on this screen, and then get into a little bit of PPU programming. We've talked about scrolling a few times in the past. We can store the equivalent of 2 full screens worth of backgrounds in VRAM and access them from multiple addresses. We have a mirroring type that determines which addresses refer to which name table. This basically sets up how our 2 screens are stitched together. Super Mario Bros. Uses vertical mirroring because we want our 2 screens to be stitched together so we can scroll horizontally and load graphics as Mario moves to the right. For more details on this operation, see the Scrolling with Super Mario Bros. Video. Mega Man 1 and 2 work in a similar fashion. We have 2 screens worth of graphical data using the 2 name tables with vertical mirroring. This lets us scroll horizontally. New graphics are loaded just off the screen in the direction we are moving. When you activate a menu, that menu replaces the background tiles inside the current scroll windows area. In fact, as a bit of trivia, the per-pixel scrolling ability across a tile-based grid on the NES means the menu appears in a slightly different location on the TV depending on the scroll window offset relative to the background. If you've never noticed this before, I'm sorry. Anyway, they use traditional scrolling and their menu locations take over background tiles. Now, as for Mega Man 3, things changed gears perhaps more than you think. Of course, we still scroll horizontally, however, the implementation is quite different. We scroll horizontally and use horizontal mirroring. That means we don't have a second name table available to use as a graphics buffer for loading level graphics during scrolling. The game has to load graphics using just one screen's width and therefore scroll onto itself. We need at least one 8-pixel wide column to hold the next set of tiles just off the screen so we can scroll them onto the screen. But again, we only have one screen's worth of graphics. So, we sacrifice an 8-pixel wide column of graphics and use the PPU's masking feature to hide the leftmost 8 pixels of the screen. You'll notice that the leftmost column in Mega Man 3 is always solid black, and this even includes the stage select screen. Line up Mega Man 2 with Mega Man 3, and you can see that we are indeed one column short. If you've never noticed this before, I'm sorry. A single byte in RAM holds the 8 bits that are sent to the PPU mask register. That makes it easy to re-enable backgrounds and sprites in that leftmost column. We just edit the value in RAM. Now when Mega Man walks to the right, you can see the next right column of tiles already loaded up inside the leftmost column. It makes sense that we would want to hide a column of graphics that was sacrificed for scrolling in order to remove this visual anomaly. Capcom previously used this technique as well as the MMC3 chip for codename Viper in February 1990. Perhaps code from this game was copied and modified for Mega Man 3. We'd have to check it to find out. Horizontal mirroring paired alongside horizontal scrolling is not exclusive to Capcom. Other companies use this technique, and it isn't something that requires the MMC3. Now, all of this is interesting trivia, but the questions are, why use it and what benefits does it provide Mega Man 3? If we have a second name table's worth of VRAM available for additional graphics, we can render the pause screen inside it and scroll it up onto the screen as a fake overlay. While it looks like we have overlapping screens, the PPU renders the playfield from one name table, an interrupt occurs, the code tells the PPU to use the second name table, along with a few other details, and the PPU renders the remaining graphics using that second name table. They must have really liked this feature because paging requires the menu to scroll off the screen and then return with page 2, whereas Mega Man 2 would simply swap the pages immediately. Note that Mega Man 4 dropped this scrolling menu in favor of a full screen system. Meanwhile, there are multiple graphical issues with this menu. Perhaps the most obvious is the scanline containing dancing pixels. This menu should be static with a border, but there is flicker on the top line. We are missing some of the top rows of pixels from those top border tiles. There is a right border, but no left border. The reason? The left border is behind the mask. The bottom and right borders that work are kinda lost to overscan anyway. All of that said, it works. Let's see what is causing the weird glitch on this scan line. The event viewer illustrates when certain things happen by drawing boxes on top of the graphics for the current frame. Time is moving forward as we move from top to bottom. This yellow box inside the horizontal blanking period is the moment the scanline count-based interrupt occurs. After the player presses start, the scanline count for the interrupt is changed frame after frame in order to scroll the menu up onto the screen. With the menu up, the interrupt is on scanline 175. Right off the bat, we can see that it doesn't always occur at the same exact moment in time. There's a little bit of jitter. This jitter changes the moments in time when the PPU register writes occur. Those writes change the graphics on the screen, and so the graphics appear to have a jitter. The solution is to waste CPU cycles in order to push the appropriate PPU register writes into the next horizontal blanking time. Make the change between scan lines as best we can. That's an easy fix, and we will take care of it in a bit. The slightly larger bug of the bad border has to do with the order of these reads and writes to PPU registers. Time to dabble in NES graphics programming. We write code for the CPU to execute. When it comes to telling the PPU what to do, we have to send values through an intermediary and wait for the results. The PPU has registers exposed to the CPU. We can write these registers in code, and the PPU will take the values, place the necessary bits inside its internal registers, and make things happen at the moment in time it was designed to do so. Timing is one of the most important things here. When you think about scrolling on the NES, you probably think of X and Y coordinates for a single screen. That makes sense, but behind the scenes there is more than just one screen, isn't there? We have 4 logical name tables and need to select one of them. A single name table is made up of a grid of tiles that is 32 by 30 in size. Each tile is 8 pixels by 8 pixels. This is your drill down approach to positioning the camera. We can specify values to indicate which name table we are using, which tile we are using, and what our X and Y pixel offsets are inside of that tile. The PPU will handle pixel evaluation of backgrounds versus sprites and spit out each pixel to the screen in analog video format, of course, scanline after scanline. Thankfully, we don't have to program that. But when we want to tell the PPU to change the horizontal scrolling position in the middle of drawing a frame, or tell it to jump to a different name table and perform split-screen vertical scrolling in the middle of drawing a frame, knowledge of PPU timing is crucial. And the crude short answer of what went wrong with Mega Man 3's menu design was that programming used the same order of PPU register writes for the menu interrupt as are typically used to set up the next frame during vertical blank. In a loose way, what the PPU does for us is different at the end of vertical blank as we start the next frame of video versus at the end of a rendered scan line, or in the case of Mega Man 3, in the middle of a scan line. Let's talk about how the PPU registers in our code map to the PPU internal registers. It will help us walk the logic executed during scanline 176. The bits of the internal registers represent a location in VRAM. V and T have the same layout. The 2 bits that represent our current name table go here. We select a tile location in the name table with values that we call course X and course Y. Finally, our pixel offsets in the current tile go here for fine Y and here for fine X. There is your layout of bits. We can use register writes to change these bits, and the PPU will take things from here. Why do V and T have the same layout? Well, V is VRAM and holds the current VRAM address. T is a temporary VRAM address. As we write new values to the PPU registers, the PPU stores those bits here until an appropriate moment in time when values are copied from the temporary address to the actual VRAM address. Which values are copied depends on where we are in frame time. Having a temporary space makes sense. Let the PPU handle the timing of copying values from T into V. But why is fine X by itself? Is there no temporary space for fine X? As a matter of fact, there isn't. If your code changes the value of fine X in the middle of a scan line, that new offset is used almost immediately. Mario 3's match game has a bug related to this. Code to change the scroll location for the next section is executed as the PPU draws the last line of the previous section. That code occurs early on the scan line. Fine X is updated almost immediately, and that results in a bad fine X offset for the remainder of that scan line. Gamers aren't likely to notice when the match game is running at full speed. Ideally, Mario 3's code would wait until after the current scan line is drawn before writing to a PPU register to update fine X. Speaking of writing to PPU registers, how does all this work? With the menu screen opened in Mega Man 3, code executes as we move across scan line 176. The game reads the PPU status register, changes the VRAM address with 2 writes to the PPU address register, changes the tile set with a write to the PPU control register, and finally resets the scrolling window, or so it thinks, with 2 writes to the PPU scroll register. If we were starting a new frame and the sequence were performed during vertical blank, we wouldn't need to worry about glitches. However, in this case, we see the work happening as the PPU is still drawing to the screen, and even then, this write sequence is incorrect. I'll explain it, and we'll fix it. First up, we read the PPU status register. The reason is because we want to reset the PPU internal register W. Yeah, waited to tell you about this one until it was relevant. You can see that we write 2 bytes to the address register here, and 2 bytes to the scroll register here. That looks a little weird, doesn't it? We're writing 2 different values to the same place? How does that work? Don't think of the PPU registers the CPU accesses as physical locations like RAM. They're just a message conduit of sorts. The PPU takes the values written to these registers and places their bits in different locations in the internal registers. The destination depends on the value of the W register at the time. So, when W is 0, bits written to the address register go here. After that write is performed, W changes to 1. Now that W is 1, bits written to the same address register go here, a different place. After that write, W is 0 once more. The same rules apply to the PPU scroll register. Bits go here when W is 0, and W is then changed to 1. Bits go here when W is 1, and then W is changed to 0. Yeah, both the address register and the scroll register require that same internal register W for the PPU to know where to put the bits. We can't access that internal register W directly. Only the PPU can do that. However, reading the status register will set it to 0. So this early action is pretty standard practice to make sure our write logic can execute while knowing what W is at any point in time. Now for the writes. The goal of these writes is to change everything by getting the PPU to jump to a different name table, tile, and XY pixel offset to draw the menu graphics. With W reset to 0, code uses the address register to change the VRAM address. Each of the 2 writes to the PPU address register has a quirk. The address we write is 2AC0. That's the starting location of our menu graphics in a separate name table. The first write is the high byte, 2A. Those bits go here. This alters the name table location, the upper bits of coarse Y, and fine Y inside the internal T register. As part of this write, the highest bit of the fine Y location is set to 0, regardless of the value we provided. Why? We don't know. But it happens. There's the first quirk. Notice that temporary fine Y is now 2. This will be very relevant in just a bit. After this write, W is now 1. With W set to 1, we write the low byte of the address to the PPU address register. Those bits go here. This alters the remaining bits of coarse Y, all bits of coarse X, and does not alter fine X. As for the second quirk, writing to the PPU address register with W set to 1 will not only write these bits to T, but also copy all the contents of T to V. We jump name table locations in the middle of the scan line, and we do so with an unchanged fine X value and a fine Y value of 2. So now the PPU continues drawing the scan line from this new location, what is supposed to be the starting location of our menu tiles. It looks like we just see glitchy garbage graphics here. These pixels are from the new location, all right, but they come from the wrong tile set. Not only that, but remember, we have a fine Y value of 2. So that means we are not only seeing the wrong tile set, but also the wrong Y pixel offset. This stretch of pixels come from row 3 of that wrong tile set. The next lines of code are responsible for setting up a write to PPU control in order to change the tile set to the correct one. Obviously, the PPU needs to keep drawing while the code is executing, and it takes time to execute these instructions during that draw time. So we just have to wait until the tile set is corrected. If we walk the code in the debugger, watch what happens after we execute this write to PPU control. We are now using the proper tile set, and the PPU uses it to continue drawing. Of course, it draws with that bad fine Y offset of 2. Finally, 2 writes of 0 are performed using the PPU scroll register. With W equal to 0, the first write sets coarse X in T and sets the fine X register immediately. W is now 1. With W equal to 1, the second write sets coarse Y and fine Y in T, and W is now 0. Wait a minute. We just changed everything in T to 0, except for the name table. Did you notice that? Unlike when we performed a second write to the address register, this second write to the scroll register does not copy all of the values from T to V. This is our last write to a register before a return from interrupt. We let the PPU go about its business at this point, and guess what? The PPU doesn't care about the Y values in T. At the end of the scan line, the PPU advances the Y location plus 1 pixel in V so it can start drawing the next scan line. Our wrong Y offset of 2 gets incremented to 3, and we just keep drawing down the screen. As for the X locations, the PPU uses T to know where to go next. We set coarse X to 0 so it knows to return all the way to the left side of the screen. Turns out we already set it to 0 with our address write, but that's okay. What we did get from this was a reset of fine X to 0. This was important because if we didn't do it, the menu drifts across an area spanning 8 pixels, depending on where Mega Man is standing relative to the name table background, similar to our Mega Man 2 menu offset example from earlier. Now, there are several finer points to know in regard to PPU rendering, but this is enough for now. So our bugs consist of copying T to V too early within our series of writes, and this results in an improper fine Y offset, jumping name tables in the middle of drawing a scan line, and changing the tile set in the middle of drawing a scan line. So first of all, how do we deal with this improper order of writes for address and scroll? The value of W matters when we write to both the PPU address register and the PPU scroll register. We need to perform these writes so that all the bit values we want are inside T just before it is copied to V. The solution is to weave these 4 writes together in an order still compatible with W. Reset W to 0 and write the high byte to the PPU address register as usual. Remember, this forces the highest bit in T to 0. With W set to 1, write the Y location to PPU scroll. This sets our fine Y location to the correct value before the copy occurs. Now W is back to 0, and we can write the X location values to PPU scroll, let them fill in the rest of T, and set fine X to 0. With W now 1, write to the PPU address a second time. This will overwrite coarse X and some of coarse Y, but also copy all of T into V. Put simply, these PPU scroll writes in the middle of the pack manage to sneak in the proper values for fine X and fine Y before everything gets copied into V. Our first update to the code might look like this. The first writes to PPU address and PPU scroll are inconsequential as far as video output, so we put them up here early in the process. After that, we work toward our tile set change. After that is the write to PPU scroll that changes fine X almost immediately. After that, our second write to PPU address copies everything from T to V. Due to the nature of overlapping bit writes, I added a write of 80 hex to the Y location for PPU scroll in order to make sure things stay on track. Could you optimize this code, perhaps combine and streamline some values? Sure. But using what is almost the same code, minus my little 80 hex tweak there, and putting it in a different order illustrates a drastic difference in output. To push these writes to a later point in time on the same scan line, all we need to do is waste CPU time. That can be done by iterating through a loop just a few times before executing our writes. A decrementing loop with just the right starting index value should do the trick. All of the register writes with immediate consequences are pushed into horizontal blank. The menu works, and the glitch is gone. Since we not only bumped the start of the menu to the next scan line, but also started at the correct fine Y offset of 0, the menu appears much lower on the screen versus where it used to be. Perhaps we should subtract a few pixels from our IRQ's final resting place so we draw the menu higher on the screen. We can save our changes and load the game on a flash cart to see the fix on real hardware. There we go. We could tweak sprite locations a bit, or perhaps even move the left side border out from behind the mask, but this should do for now. Now let's return to this, the Mega Man 3 stage select screen. Why did I save this one until the end? The reason this glitch exists is because of unnecessary code for this second split. The screen is split twice, so it shows up in 3 sections. A horizontal scroll split is all that is necessary to accomplish the desired effect. The player presses start. All 3 sections scroll together, and the game repaints the entire screen of tiles inside a separate name table. In fact, this results in a noticeable delay before the player sees the bosses appear and regains control. With the tiles drawn, sprites are used to construct the faces of the bosses. We switch from the old name table to the new one, and there's a noticeable jump in the bottom third's offset when this happens. And the boss select screen has been reached. The glitchy line just above Shadow Man's head is quite distracting. Perhaps it is distracting just enough that you don't notice that there is a background tile issue in the top right corner. The left half of M in Mega is missing. There's more going on for this lower third than just this glitch. We are missing a scan line. This is noticeable for the round circles at the top of the boxes for the lower 3 bosses. You can also see how the Roman numeral 3 has a line of pixels shaved off the top. This problem sure seems familiar. The obvious question is, why is the split between the top and middle third fine, but the middle to bottom third split has this glitch? The reason is because the upper transition uses writes to the scroll register alone, whereas the lower transition uses writes to the scroll register and the address register. Oops. We don't need to write to the address register here. There is no name table jump like there was for the menu. We just need another pair of writes to the PPU scroll register, just like the upper split. Was it a copy-paste issue from the menu code or elsewhere? Who knows? You can use a Game Genie to change the PPU address writes to reads and therefore disable the code, and that fixes the jump at the end of the transition as well as the line glitch above Shadow Man. The side effect of this fix, just like the menu, is that sprites used for the faces are now in the wrong place. So, those sprite Y locations should be increased to fix the faces. While we are at it, why not also correct the tile table so we have an M up here? We could even unmask the left side column if we wanted. And there it is. I hope you've enjoyed this dive into graphical glitches of Mega Man 3. Please like and subscribe if you'd like more videos like this one. I also have a Patreon available if you are interested, and thanks for watching.